So hello everyone. My name is Carlos Lizárraga, and today I will be talking about time series and how to um, work with them, doing all the time series analysis, and a little bit of data time series forecasting. So this is a very specific topic to every science that collects data, uh, and it's ordered in time. So it can come from different sensors, can come from different recordings, and there is a whole new field in data science for working with time series. So the importance of the time series is that it's a sequence, a very ordered sequence, and also we assume that the time sequence is uniform. If you have a non-uniform time series, then you have to um, do an interpolation in order to have the same time lapses between the data. And also, if you're working with different time series and you have to, at some point, when you join them, try to have coincidence in the time lapse or time um, sequences. Okay. Time series is a discrete time uh, data, and also you can have continuous data, assuming you are scanning your data continuously. Like for example, if you're measuring your ocean tides, and your resolution is like taking measurement 20 times per second or once every minute, then you will have different time series. But usually when you have different sensors, what you do is just work with whatever resolution your equipment gives you, and then after that you can reprocess or post-process and then extract time series sampled every minute or average every 5 minutes if the physical process doesn't change that much. For example, ocean tides or some other uh, some other quantity or phenomena. Um, so you will find time series in signal processing, pattern recognition, econometrics, finance, weather forecasting, earthquake predictions, and many other fields in applied science. So how do we work with time series? Uh, so when you're working with time series, you will see, for example, let's say we are studying climate change or weather patterns, and then we will see, for example, if we analyze the temperature of, let's say, Tucson for the last 100 years, then maybe we will find a trend that the temperatures are increasing, the maximum temperature is increasing, or the minimum temperature is also increasing. So we will have more warmer mornings. And then there may be seasonality, so the temperature is different by seasons. And also you may find like cyclical patterns in some phenomena. You can also do frequency domain analysis, and this has to do, for example, doing Fourier analysis. So Fourier analysis, let's say you have a sound wave coming from a string from a guitar, then you can, if you do a Fourier transformation of the signal, you will find that there are some fundamental modes in a sound coming from a guitar or a piano. So you may find that if this is a linear analysis, that whatever wave can be decomposed as a superposition of different waves. And you just need to know what is the mode, the basic modes of this signal. You can do stationarity and non-stationarity, meaning that some series, in order to do the composition and see if there is a trend, you need to have a non-stationary, stationary time series. You can study autocorrelation. You can have different models for time series. So for example, when you're trying to do a forecast, then you have to create a model for your time series. And these models, you have different options like ARIMA or seasonal ARIMA or exponential smoothing models. And even today, some people use neural networks in order to do time series forecasting, but in that case, you have just a black box and you input your time series data and then it will predict something. Okay, you can have multivariate time series analysis. Let's say you have different variables and each variable is changing time. Like for example, if you have a weather station, you are measuring temperature, atmospheric pressure, relative humidity, etc. Okay, when we have to work with time series in Python, we have several options for doing the analysis of the time series. One of the basic libraries is going to be stats model, that it will include different time series models in order to work with your time series. There's other libraries like stat forecast, and then you have the classical pandas for working with your time series. Sometimes you just get your data set, and the data set includes a column or several columns that involve time. For example, you may have a data set that involves the year, separated then by the month, by the day of the week or day of the month, and also you may be including data every 5 minutes or every second, and then probably you need to combine the different columns into a single time variable in order to work with your time series. Other libraries, skTime, like the scikit-learn. Also, you have the PM-ARIMA, which is another model for doing statistical analysis. Okay, you may find different libraries. You have Profit from Meta. Also, it's also a neural network for analyzing time series, and so on. So we will show you some examples using statistical analysis of time series. When you're talking about time series, for example, you will find that people talk about trends. So this is a plot of the atmospheric CO2 levels measured at the Mauna Loa Observatory. And this is how the CO2 has been increasing in the past since they start measuring around 1960 up to date. And you will see that the parts per million of CO2 has been increasing from 320 parts per million up to more than 420 parts per million. So this is a clear evidence of the increase of CO2 and also the consequences of global warming. Also, we can find seasonality. So for example, we can see how something is changing by seasons. So it's different during the winter than during the summer. And also, for example, here we have a measurement of the sunspots over the solar cycles. So it repeats every 11 years. So this is a plot of the different sunspots, and it's correlated with the sun activity. Okay. We mentioned about stationarity and non-stationary time series. So this is a stationary time series. So you can think that the average is 0, and a non-stationary time series, then the average is changing against time versus time. You will find there are different tests for doing testing if a time series is stationary or not. So we have the Decay-Fuller test. Also, if we want to convert a time series into stationary, then maybe we can apply differentiation. So when we apply a differentiation to a time series, we can make it stationary. Also, we can talk about decomposition. So decomposing a time series means splitting into different parts, the trend, the seasonality, and also some residual or noise. Okay. Another concept that is used in time series is just moving average. So a moving average is just a smoothing of your time series. For example, if you're looking at the stock exchange for some stock, you will see that the variation can be, a stock can be changing by the hour, by the minute. But then when you do a moving average, then you can just look at a smoother curve and tell if something is increasing or decreasing or changing across the time. With moving averages, we can create models for the time series, and then these moving average can be combined with other parts like autoregressive models, and also integrate all the information to create a single model. So we will see an example of that. And then we will have different tests to see if a model satisfies some hypotheses, and we will try to select the best models following some criteria, like the Akaike information criteria for the best model. And so we will look at the ARIMA model and the SARIMA model and some other models. Okay, so this is very general. If you have done time series and you have read something about time series, then you can find that many groups are using different models for trying to make forecasts, time series forecasts. So you will find ARIMAs, ARIMAX, and these are the different meanings and different combinations of methods. So you are in the ARIMA, you are combining autoregression and moving average and integrating. And also in the SARIMAX, you are combining seasonally, autoregressive, integrated moving average with some external variables, etc. Okay, so with no more discussions, let's go to open this Jupyter notebook, and we'll do an example using different methods and also different techniques in order to do time series decomposition and also create a model for creating a forecast for a time series. So let's open this notebook and then open it in Google Colab. So you will find, let's go back. You will find this Jupyter notebook, open it in Colab, and tell me if you have, if you're there. Okay.
I'm there.
Yep. Okay. So we're going to analyze the CO2 levels in the atmosphere. So first we will need to load some basic Python libraries. So we're going to import from pandas select series, and also NumPy, pandas, matplotlib, and seaborn for visualization, pandas for data analysis, NumPy for mathematical operations. So we execute the first cell, and once it has finished, then we're going to import the CO2 data from my GitHub. So I'm just going to load it and define a data frame dfdist, just reading CSV data, and I'm going to print using the get function the first 5 rows. So this is the data for the CO2 concentrations. We have year, month, decimal date, the average of CO2, the CO2 without seasons or deseasonalized, the number of days for the measurements in that month, the standard deviation, and the uncertainty. And remember that now Google Colab recommends you some plots. So if you have a data set or data frame, then you can see different types of plots you can create.
All the recommendations.
Yeah, just recommendations. So now, if you're not using Google Colab, there's a package for Jupyter Notebook that has the AI integrated, so it will respond similarly to what you're getting here. Okay, so I'll continue doing the traditional analysis by hand. So I can print the last 5 rows using the tail function. So my data go up to February 2023. I haven't updated my data set. Then I can do the info function to tell me what's the general overview of my data frame. So I have 8 columns. These are the names of the columns, and have 780 rows. And this is the type of data. So year, month, decimal date. Year and month are integers. Decimal date, the average of CO2 and the seasonalized CO2 are just into decimal numbers or floating numbers, 64 bits. The number of days is an integer of 64 bits. The standard deviation and the uncertainty is just floating, 64. I can do statistics on the numerical variables using the describe function from pandas. So it gives me the number of rows, the mean, the standard deviation, the minimum, the maximum, the median, the first quartile, and the third quartile position for every column. We can use Seaborn to plot the time series. So I'm going to define some settings for my plot, like the figure size. I'm going to use white grid as a style, and then I'm going to use Seaborn line plot for my decimal date in the x-axis and the average CO2 in the y-axis. And I'm going to use color for the years and set some labels on the x-axis, the y-axis, and title. So I execute, and I will get how the concentration of CO2 has been changing across the years since 1960 up to last year. And just changing colors. So we can see here, this is a time series changing, but also we can find there is a seasonality associated with my time series, and also there is a trend, increasing trend. But we have to prove that that's the case. So we have to use additional statistical tools to decompose our time series into 4 parts. So we have the time series, and then we can have the trend, we can have the seasonality, and also after everything else is accounted, then there's all going to be a noise or residual. So we're going to use some statistical tests for doing that. Okay, before doing that, I'm just going to be interested in studying the last 30 years. So my time series comes since 1960, so I'm just going to analyze the last 30 years. So from my data frame, original data frame, I'm just going to select data for the years greater or equal than 1992 up to 2022, and then I'm going to plot. Going to create a similar plot, but just now concentrated from 1992 to 2022. So this is my plot for the CO2 variations in the last 30 years. Okay. So we continue. Now, we're going to use exponential smoothing to create a model. And we're going to use this Holt-Winter seasonal method to see how to decompose our time series. And the time series, the composition can be additive or multiplicative. So we have to specify. So we're going to import regression model from stats model for Seaborn, and also we're going to import stats model and call it SM, and also some stat model time series analysis API. We're going to import exponential smoothing model and a simple exponential smoothing, and also a hot smoothing. There's several ways you can smooth your time series, and basically it will depend how many points from the neighborhood you're taking into account in order to compute an average. So for example, let's say you have a time series and you're trying to compute, let's say you're looking at the monthly variation of CO2, and I can say I'm going to take an exponential smoothing average considering the previous 11 months in order to compute the exponential smoothing average at the 12th month. So if I include 11 months, I will have smooth my time series using 12 months of data. Okay, so I import the libraries, and then I'm going to create a simple time series just from 92. January 92 to December 2022, and the frequency is monthly. And I'm going to define a new, the new range, just looking at the average. And I'm creating from my data frame, I'm just going to take the data and the index and create a series, and I'm going to call it EFCO2. So the time series now, just looking at I don't have the data frame anymore. I just have a time series, and the index is just the time, and the value is just the CO2 average monthly concentration. So now I have a time series, and then I'm going to try to create a future forecast model using 36 months ahead in the future. So I'm going to fit the exponential smoothing model into my time series for CO2 concentration, monthly concentration. And I will assume that the CO2 variation is influenced by the seasons. So I'm going to be taking into account 12 neighborhooding that data in order to create my model. And I'm going to assume that the trending is additive and the season is multiplicative. And also, I'm going to select these parameters estimated for the initialization method. And then I'm going to fit the model. So, and then after that, after I have fitted my model and created my simulation for the number of months, which is 3 years, and I'm going to repeat 100 times, and I'm going to assume that the error is multiplicative. Then I will have a simulation, and then I will plot my simulation using the plot function from pandas, and select figure size. The marker, I'm going to use dots, black dots, and I'm going to assign some title for the forecast and simulations from the hot winters method. Set the Y and X labels, and also I'm going to make another plot for the fitted values, and I'm going to plot using a line, dashed line in green color, and also I'm going to plot the simulations using dashes and transparency of 0.05 in gray. And also I'm going to overplot or overlay the plot for the forecast for 36 months using the hot winters model method. I'm going to plot what is this model predicting for the next 36 months after my time series have ended. So I now execute it. And now I have my original data, the simulated data, and also in the last part for the last 3 years, I'm trying to predict how the CO2 monthly average concentrations will be for the next 3 years after 2022. So this is how I'm doing a forecast. So the forecast is telling me that it will continue increasing, and also it will be continue showing this seasonality. And so now I have predicted a forecast for 3 years after in the future from February 2022 um, up to 2025 February. Okay, so that's one model, the exponential smoothing and the whole winter's seasonal method to make a forecast in the future for your time series. Okay, another method is the non-seasonal ARIMA models. And so I will assume that my model doesn't have any seasonal component, but I'm going to apply it. So what is the ARIMA? So ARIMA is autoregression. So what is autoregression? Regression is just a regression or fitting a curve to a set of points. And then you're going to combine it with moving average. That means that if you have a time series, then you will have a smooth time series. And the autoregression will have an index called P, or a parameter called P, and the moving average will have a parameter called Q. And then we combine these two besides a differentiation, which is denoted by the D. So uh, the ARIMA model will depend on 3 parameters: the P, which is the autoregression coefficient, and the moving average coefficient Q, plus some derivative. And the derivative is just to make it make your one technique of making your time series into a stationary time series is applying differentiation. Okay. And then we can use this library, the TK Fuller test, to decompose your time series. Okay. So now I'm going to be importing other set of libraries. From the scikit-learn metrics, I'm going to import the mean square error and mean absolute error. From the stats model, I'm going to import the API. And also from the stats model, I'm going to import time series plots, time series analysis plots, and I'm going to import these two libraries, plot ACF autocorrelation function and the partial autocorrelation function. And I'm going to import Sarimax. I'm going to import this ARIMA process, graphics, time series analysis stat tools, add Fuller, and time series analysis ARIMA model, the ARIMA results, and ACF and PACCF, which is autocorrelation function and partial autocorrelation functions. I will explain visually what do they mean when we do the analysis. And then I'm going to import this TQM-DM method library, iter tools, and some other libraries. Okay, so I'm going to import a set of libraries in order to make my ARIMA analysis. Once we do that, then we can continue trying to process our data. So again, I'm going to plot my time series for CO2 monthly average concentrations. And so I have my plot as before. And also I'm just analyzing from 1992 to 2022. Okay, so now we're going to apply the add Fuller method in order to decompose my data frame or data set time series. So we apply add Fuller function to the time series, and we're going to print there's a p-value that the add Fuller method or library gives you, and if we are doing hypothesis and assumptions, we need to have a p-value less than 0.5 in order that to claim that the time series is stationary. And since the p-value is greater than 0.5, then I cannot assume that the original time series for the concentration of CO2 is stationary. So I need to fix it or convert it in order to make it stationary. So since our time series is not stationary, I need to differentiate. So I differentiate one time. So I'm going to take the derivative for the time series, and I'm going to call it TFCO2 differential. And then I'm going to apply again the add Fuller method to the differentiated time series and see if my p-value improves. And then we can find that the p-value is less than 10,000 or 10 to the minus 4. So now if I have differentiated one time my time series, I have a stationary time series. Okay, so now I can create with the stationary data time series, I can create a model for doing predictions. Okay, so we have d equals 1 because we have differentiated one time. And then we're going to do a model. So we need to split our data into training and testing. And we're going to, from the time period, we have our time series. Then we need to reserve, let's say, 36 months, the last 36 values in order to be the testing data set, and train our data with all the rest of the data. So we do that, and we have 336 data for our training, and we have 36 or 3 years for the testing. And so the time series has a length of 372 data in total. Okay, so now we're going to use ARIMA to find the appropriate parameter values P and Q, the autoregression, and also the moving average. So we define a couple of functions. We have this optimized ARIMA, and it will try to compute all different combinations of P and Q in order to see what is the best model, and the best model will be that has the least or the smallest or the minimum IQ information criteria. So we do that, and we'll get a table of results, right? Okay. And then we will have, this is just the function definition. And then we will see, okay, now let's try values for P and Q from 0 to 4, increments of 1 and 1 derivative. And then we have this ordered list. And then now we are going to optimize for the different values of P and Q and see what is the best result. So now we are optimizing the ARIMA, and then we can see combining P and Q. This is the AC criteria. So I'm looking for the one that has the least value of AIC. So 2 and 3 seems to be the best choice, because every other combination of P and Q has a larger AIC value. Okay. Okay, so I know now that my ARIMA has to have a P of value of 2 and a Q value of 3. So this is the autoregression, order 2, and the moving average of order 3. That means I need to include 3 points. Okay, so now I have 2, 1, 3. This is P differential and the Q. And then I'm creating a model called model 1. I'm going to use the training data in order to, and then fit our model with the training data and then print the characteristics of the SARIMAX model. So we have 336 observations. This is the model, 213 P1 PDQ, and we need to look at the where's the AIC value? The AIC value is 659. There's another criteria called BIC. Don't remember what it means, but
You have a question in the chat.
yes. You give a range to test your P's and Q's, and then you do this loop in order to find what is the best value. And the best value will be the combination that gives the least AIC value. So you just give a range and let the algorithm optimize and compute the AIC for the different cases of P and Q. And then that's how we came up with the 2 and 3. So this is one way of doing it. I will show you. Yeah, you can do 0 and 5. You will get the same result. Let's say, okay, let's play with between 0 and 5 and do the optimization, and I should get the same result. It's just a range, right? So the list, no, I have now a different value. I have 4, 4. Okay. Well, your result is not definitive. You're just searching in the parameter space. What if I do 0 to 1,000? Maybe there's another option that give you a less value for the AIC, and then you stick with that. So 4, 4 is a good one. If I say from 0 to 10, maybe I can find another option. It's not the unique answer. You're just going to have a model that has some precision or accuracy, and then you stay with the one that gives you the least value for AIC. So I'm trying now from 0 to 10. I may have another value. Okay. So it's like you're creating a model to create a forecast, and your model can be improved, of course. And so I'm testing from 0 to 10. Okay. And whenever you create a model, you will talk about the precision and accuracy of your model. And it doesn't make sense to be looking for, you just want to have an answer, an idea if the things are going to be increasing, if the trend is going to continue, and probably you will try to make a forecast. Of course, the forecast cannot be for 20 years. It's just a forecast for a couple of months because you don't have too much data. Okay, so it's taking some time. Almost there. Okay, about to finish. So do we have a new answer, or we stay in 4-4? 8-9. Okay, it's another answer. Okay, I don't remember what we had in the 2, 3. Okay, so we can have 8, 9, it doesn't matter. Um, and then we c- we just have a model. It's not the perfect model. Okay, and then you still, when you run the Sarimax, you still need to look at the AIC 659 and the p-value. I don't know if you get it here. Yes. Um, okay. Okay, for the sake of computing, so now we have the 8, 9. We can go and change here from 8, 9. Doesn't matter, really. It's just a model. There's no perfect model. And then, so we have the AIC of 318, and these are the some parameters for the autoregression and for the moving average, coefficients, standard error, the C value or the C transform, assuming that you have a normal distributed variable. Okay. And then you plot your model, and this is the standard residual. So this is a stationary time series. This is the uh, kernel density estimate and the histogram for your values. For your values, this is how the QQ function for a normal distributed function, and this is the correlogram. So the correlogram has the relevance that it tells you how a specific value depends on the previous values. So actually, when we do the autocorrelation functions, we will see clearly. Okay, so let me continue. So now we're going to use a graphical method for determining the values of P and Q. And I guess the idea is to get the first crossings or the first time P and Q. Um, well, you will see. So I'm again, my temporary data frame is just the differentiated CO2 stationary time series for the column CO2. And then I'm going to put a number of lags in order to compute an estimate for P and Q. Okay. And I get these plots. So this is the partial autocorrelation function and the autocorrelation function, and the autocorrelation function, the partial gives me a value for P, and the autocorrelation function provides a value for Q. So graphically, you're going to look for a value of P when this curve crosses the 0. And also you're looking for integer numbers. So this function crosses 0, and so my best guess for P is 2, and my best guess for Q is going to be 3. So this is again 2 and 3, which I had before. And of course, maybe there is another plot further down the road. But anyway, this is a graphical way of doing it instead of doing this other algorithm for optimizing your model. So at least you have two ways to check. And then we have this function to test if a time series is stationary or not. And just using rolling mean or moving average and a window. So I'm going to be computing a moving average with a window of 12 months. And then I'm going to print the results of the decay Fuller tests. I remember it will give me a p-value if it's stationary, less than p 0.5 and it's not stationary, then it doesn't satisfy. So I'm going to test the stationarity of this function, and this is the moving average and standard deviation of my time series. Okay. So we have a rolling mean of 12 months, almost stationary. And then the p-value is less than 0.5. So I can safely assume that my time series is stationary. And the number of lags used was 13 months. I have 357 observations, etc. So I'm going to now decompose my time series into different parts. So I'm going to use the time series analysis from stats model and do the seasonal decomposition of the time series. Okay, I'm going to use a period of 12 months because 12 months is a year and the time series seems to be changing year by year. Okay, and then this will plot the components of my time series. So I have four things. The first one is just the original time series, the observed, from 1992 to 2022. And this function, the seasonal decompose, also gives me a trend. So I can now affirm that the CO2 levels monthly average is increasing with the months. This is the seasonality. So I can see that year by year, my time series has the same behavior for spring, summer, fall, and winter. So it depends on the season. And this is the residual. So this is what is left. So the sum of this time series plus this one gives me the original. So these are the three components of my time series. Okay. And this is a stationary time series. Okay. So I'm going to look at the residue and then test the stationarity of the residue. So this is the residue, and applying the stationarity function for testing my time series, I can see that the p-value is less than 0.5. So the residue, when you do a seasonal decomposition of your time series, the residue is always a stationary time series. And in order to create a time series forecast, you need to have a stationary time series. So of course, you have a trend, you have seasonality, but you need to have a stationary time series in order to create a model. Okay, so we have the next two models, the ARIMA and the SARIMA. And okay, so I'm still playing with 2 and 3. And then I'll make my model using the SARIMA and make predictions. And then I have the predictions. Okay? And then I can see what is the actual time series and the predictions, the predicted means. So I have the ARIMA did not give me a very good answer, okay, because I'm not including the seasonality. So I can do another prediction and I have different values, okay? So I'm going to plot how is my prediction and confidence intervals in the future. So you can see this is the original time series and this is the prediction using the ARIMA. Okay? And I have the confidence intervals. It doesn't show very well, but it's a very light pink. So this is the the confidence intervals. Okay, so instead of using the ARIMA, this is my forecast. I will use other model, which is called the SARIMAX. So I need to install it. I do. And then after I install it, I import the SARIMAX. And I'm going to play with different parameters. So it's going to optimize, and I'm going to use the information criteria for my key. And then it's playing with the different parameters, and I need to select the one that has the lowest AIC. So the best model is SARIMAX or ARIMA 00011 01112, and which is the 011. Yes, this one has a AIC criteria of 208. So that's my best model. Okay, and then that's my best model. And then I just go and play with it. So now now I know the values of the different parameters and make predictions with the second model that includes seasonality. I make the predictions, and then I will plot. You see how the difference between the blue one was the ARIMA model. The observed is in green, and the SARIMA, the model we are just using, it's very close to the observed. So SARIMA is better than using ARIMA for this case of time series that has seasonality. And then I can make the predictions then. I train my model and then make the predictions. And then you can see that the predictions are better than I had with the ARIMA. So I need to, in this case, for my time series, which has a very strong seasonality dependence, SARIMA is better than ARIMA. So I see how the forecast for how the CO2 monthly concentrations will change in the next 3 years, starting from February 2022. So this is a better forecast. Okay. And then I can predict how it's going to go all the way to 2026 and plot it. And this is how my prediction will go after my time series has finished. So I'm just looking at the future. Okay, so I think that's, yeah. I'll do the same thing just with more resolution. Looking at the window, this is how the prediction for the future, the next 36 months is going to be using the SARIMA. So SARIMA, once you have a time series that is very strong, depends on seasons, is better than just using an ARIMA model. Okay, so fast track, we have seen several ways of doing time series forecasting using different models. And then depending on the time series, the type of time series you need or you have, then you may use different options. And you have seen that there's more ways of creating one model. You're playing by the different parameters, and every model will give you a different precision and accuracy. And then you can compare, once you have the future data, you can compare how well your model was. Okay, so that's what I have today.